Okay, it's quiet enough. Let's get started. So during the break while you were working on your stuff, I was working on my stuff, and I was putting the lectures out here. So for those of you who came in late and missed the morning introduction, or you didn't come in at all today and you're not here and you're listening to this audio recording or video recording and you're going to watch this tomorrow or something, or the next day, or perhaps the day of the final exam when you're trying to figure out what the test is on, here's where it's organized for you. I put it into three different, so I'm trying to label it. So this is like the class introduction, and then we have lectures 1, 2, 3, and then we have that first exercise. So I tried to break things up, kind of make sure that they were kind of user-friendly in terms of finding it. So this is actually going to be lecture number 4, and it's a continuation. And so I'm going to go ahead and get started with it. And we went up to slide number 40. The slide set goes up to 100 and something, but it's like this. Like this is like 5, 6 slides, just going through different iterations of stuff. So it's not that bad. So we'll do a little bit, maybe about an hour at the most. A little bit of boring, listen to me. And then after that, you'll have the second exercise. You'll love the second exercise, especially if you've been paying attention to me. Because the second exercise is all in the material that I gave you this morning. So you'll love it. You'll be able to knock it out and upload it to the LMS instantly, and you'll be able to be done with today. And then tomorrow's a brand new story. So as I'm getting to the slide where I stopped, we were talking about how we apply problem solving to artificial intelligence situations. Because it's a slightly different scenario in terms of problem solving for computer science and other disciplines. So in the area of search algorithms, we're starting fresh with a brand new topic, and it's on search algorithms. And this is going to get into the informed and uninformed searching and how to go about tackling the problem. So the basic idea is we want to do it offline, which means we're going to know about the information, we're going to research it. We're not going to do it while we're gathering the data. We're going to take the data and analyze it after we've obtained it. It's going to be a systematic exploration of simulated state space by generating successor of explored states, expanding the states. So we can take a sampling of the we can simulate this space by expanding or sampling the space. What's the space? It's everything we know about the particular problems and in the particular area in which the problem is occurring. Sometimes the space is too big, so we do a sampling. And that's like taking a small portion of that space that's more manageable, and then we can search through there for a solution. And in that particular case, what we're looking for is, does something exist or does something not exist? Is this a case, like a true-false kind of thing? In terms of the general search, it kind of falls into this if we were going to look at this in terms of pseudocode. We have a general search with a problem strategy which returns a solution, hopefully, or a failure, initializing the search tree using the initial state problem. So we're going to come up with, it's either going to fail or it's going to find something. And so what we end up having in this particular case, I was waving upstairs there, is that first time I saw her, actually, we have, see, we're in class. I'm being recorded, so I better shut up. Anyway, so we're doing what we're supposed to be doing. Loop do. What does loop do mean? So if there are no candidates for an expansion, then return failure. Otherwise, choose a leaf node for expansion according to the strategy. If the node contains a goal state, then return. And then in terms of the corresponding solution, else expand the node, adding results to the nodes. This is what I'm calling pseudocode. It's not programming. It's not an algorithm. It's a solution. So in some of the questions that you're going to get in the homework that you're going to take home with you and do in between this meeting and the next meeting, it's going to ask you for pseudocode. And this is what I mean by that, by the way. So you're not writing, it's not a special language. Slide number 40 of lecture number 3 gives you an example of pseudocode in terms of what it is I'm talking about. And inevitably I'm going to have several students who ask me the question, what do you mean by pseudocode? There's no formal language for pseudocode. It's kind of if, then, else, kind of do this. This is a function. This is what we're looking for. Find this, find that. Because what you're going to do is going to analyze a genetic algorithm, and we're going to talk about that probably tomorrow. And then you're going to look at that and go, and I'm going to say, write some pseudocode. What do I mean by that? Well, it's the process you're going through. Last time we looked at problem solving, and the problem solving had some characteristics that were associated with it. So this is the problem framework. I call it a framework. Other people refer to it as by other names. It's a problem solving approach. And so what do we have here? We have the problem solving, which is looking at the goal formation, the problem formation, the states, the operators, the search for a solution, and then we have the problem formation stage of it, and then we have the problem types. The problem formations deal with the initial state, operators, goal, test, path, cost. This is vocabulary for you, by the way. This is why I'm kind of going over it over and over again. Kind of repetition is kind of the way you're going to remember some of this stuff. And if not, you'll probably remember where to find it, maybe. Which is slide number 43 of lecture 3. In the terms of the problem states, we talked about this before. This is a little bit of a review before we broke out, where we have a single state, a multiple state, contingency, and then we have exploration, which is another state that we can apply unknown state spaces. We talked about this as a sort of a review of what we talked about before the break there. Last time we also talked about the concept of finding a solution. And so the solution is, well, that's a good question. What is the solution? It's a sequence of operators that bring you from current state to the goal state. So when I say find a solution for something, it's not like a number. It's not like solving a math problem. It's the steps, the actions taken by the AI engine to solve the problem. So sometimes it's turn left, turn right, go backwards, recursively or something. There's different types of solution scenarios. That's what's really meant by the solution. It's not a right or wrong answer. It's a process. Because you can solve different tasks in different ways. If I said get in your car and back it out so that you minimize the amount of gas you take, well, there's a solution to that. Many different ways of doing it, but there's one that's going to minimize the gas that you're going to take. Also, we have the basic idea of offline systematic exploration of simulated state space, and there's a repeated definition again of the concept of the basic idea. And then this is a repeated statement as well in terms of the pseudocode you saw in the previous slide. The strategy is basically the search strategy is determined by, and that's the question we're talking about right now. How do you know which search strategy and which strategy approach you're going to take to solve the problem, to come up with the solution? Because sky's the limit if you think about it, especially if you apply different disciplines to the problem. Can you guys take the conversation outside? I feel like I'm having to talk over you. Thank you. It irritates the people around you too. All right, so the search strategy is determined by the order in which the nodes are expanded. So when we talk about a search, usually we're referring to trees, and we have nodes in the trees, and we're searching through a list, we're searching through a tree, and so we can expand them out top to down, bottom up, left, right. We can search them 2 at a time, 4 at a time. We can expand out certain areas and not expand other areas. So that's basically the strategy in terms of the search solution. If we go back and look at this traveling from Arad to Bucharest, I'm probably butchering all of these names, we could start in this direction and we would say that's probably a bad direction to go in, but it does lead us down here. We could go out this direction or we can go out this direction. We have 3 options. So the choice in which we're going to expand the nodes might be predetermined by information that we see way down here. May also not be if we're doing an exploration. It might just be expand all of them and then see which one's the most promising. So you get to a certain level, you probably get to around here. And then you figure out, well, I can only go in one direction, and you expand further. So if we take a look at this and we define the solution in terms of the problem space to the search tree, in this particular case we have the problem space, and it's very common to see the solutions written out in the form of these graphs. And this is a connection graph. It kind of looks, if you've ever done any project management and you've looked at PERT and CPM and you've kind of looked at critical path as a concept, because you guys are, some of you are business majors, this is what I'm talking about. You can find the shortest amount of time given the order of the task, and what you're doing in that particular case is the same thing you're doing here. And that's kind of an artificial intelligence way of imagining how you're going to manage projects. What you do is you come up with, by looking through the analysis of this connection graph, all the different orders you could possibly do all the different tasks in, and one order is going to give you the shortest amount of time. And that's the one you want to do because you want to save money. You want to get the project done as fast as possible, which is what you're doing here. We want to get to the airport as fast as possible in this particular example. So here's our problem space that's identified out. And then down here we have our associated loop-free tree structure, search tree. And it's interesting that this one is basically saying loop-free. We don't want to put loops in there. Loops are a waste of time, especially for thinking about going from point A to point B. Last thing you want is to have a cyclical graph that basically goes in cycles, and there's basically multiple ways in and no way out, or a loop where you're going around and around in a circle and you're not getting to the answer. It makes for a bad robot, makes for a bad travel plan, makes for bad directions actually too. But some people make U-turns just naturally because they miss their exits or something. So, but that would be a loop. So here's an example of a path in the search tree. So it's denoted by, and then we have here the denotation. So S is the start symbol. So if you're going to use this kind of notation, great. If you want to use your own, that's also acceptable, because some of the problems that you're going to have to answer are going to ask you to come up with a search tree. Show me the path. Well, in this particular case, I'd say the path is SDEBA. SDEBA, which is the red line if I just followed it correctly. Or we have this other path here, SDA, or this path here, SA. So we see written out by node numbers. The order in which we draw the nodes is completely up to our tree type. You don't have to know anything about data structures, but you could basically think about a binary tree. You could basically think about different types of tree structures that you might create, which is why a lot of artificial intelligence people or computer science, they study computer science, because if you know about tree structures, then you can kind of utilize that knowledge in terms of your things. But then we also have artificial intelligence, people that think in artificial intelligence solutions that don't know anything about trees, because you don't really need to know about the mechanics of the tree to build the tree. So here we have our situation in which we're going to build a tree. So a general search example might start out here where we have Arad, and then we have the 3 cities that we could possibly go to from this city, and then we have the cities that we could possibly go through if we chose this direction, and then we have the cities that we could possibly go to get to here. So we see a 1, 2, 3 hop to get there, which is not so bad in terms of its efficiency. So the implementation of the search algorithm, we can do what's called a queuing function. And so if we do a queuing function, this is where some of the interesting programs come into place, like Scheme and Lisp and Prolog. And we're going to use Prolog to do a family database, actually. So you'll be looking, if you don't know your family history, you don't have to worry about it, you can just make it up. But if you knew your family genealogy and your whole draft, you can actually kind of figure out how many cousins did so-and-so have, and is so-and-so actually from this part of the family or that part of the family, by creating a database in Prolog of all the different connections between all of the different generations, and then doing some analysis on it and asking Prolog some questions. And Prolog makes the connections for you, so you can kind of come back and say, oh, that's how that fits in. And you can see things a lot faster. It's an artificial intelligence way of looking at logic in terms of that. So Scheme has this thing that's built on recursive functions. So we have functions that call functions that call functions that call functions. If we took all of the different graph paths that were associated from the tree and we came up with a function, and the function did a distance calculation, and we queued up all of the different cities and we plugged them through the function recursively until it went from point A to point B, we could figure out what the distance was. And so we could use a program like Scheme to calculate this out. In our pseudocode down here, what we're looking at is a queuing function. And the queuing function is a queue and elements that we're trying to find in the queue. And the element's going to be the destination or the goal. So as a queuing function, it inserts a set of elements into the queue and determines the order of the node expansion based on the goal. So we have varieties of different queuing functions that produce varieties of different search algorithms. So Scheme, as an example, and also Lisp, has the ability to kind of create functions to queue up in this environment, and actually kind of, once you have the data, stick it through a well-defined format, essentially, and run a function. So you're automating the process, which is basically a solution to a search-related situation. So here's a way of encapsulating the state information in a node. And you're thinking, well, you can do a graph like this, and you can use nodes, and you can expand nodes in certain directions when we have a path. So it works with geography, or it works with, from point A to point B, but it also works with calculations for, let's say, for example, moves. So each one of the states can be graphed out, so we can put the states together in terms of the order of the transitions. So if we go from, square A to square B to square C, we can graph that out the same way, which is kind of interesting because most, beginning AI students, they go, well, when do we need to use a graph? Or I'm calling it a graph, but what I really mean is a tree. We have in a separate graph we can actually create out of this. When do we want to use a matrix for this? When do we want to use a table for this? And when we start talking about that, what I'm referring to is what's called knowledge representation. So that's the knowledge database and the knowledge representation of the data. And it's the computer-saved form of the data. So if you call it a matrix, put it in a form of a matrix, call it a table, a tree, a node, it's the representation. So it doesn't really matter what the problem is, it's the representation choice that you choose that's going to determine how you're going to represent it, which is also going to determine how you're going to search it, if you think about it. So certain problems, people like to do certain things a certain way, and so they'll naturally tend towards stuff. I'm not really a tree person. I'm more of a list processor. So I'll take lists and cross lists with other lists and accumulate data that way. So people have their preferences, but I can't do a list for everything. Occasionally you have to put a tree together in order to make that work properly, which is a choice. So choice, but there's an optimal solution and then there's a solution. So it depends on what you're happy with in terms of your decision making. So the state of anything is represented of a physical configuration. So we make a physical configuration of the state. In this case, a node is the data structure that's going to be consisting of part of the search tree, which includes the parent, the child, the depth. So the states do not have parents, children, depths, or path costs, actually. They just have states that are associated with it. So here we have a parent that comes down to a node, and on the node we have information about how deep it is, what characteristics it has, and then what children are associated with the node. The classical thing we get in data structures is we learn how to create a tree, take the tree and reduce it down to a list. And then we take the list and we process the list to do something with it, to calculate something out, which is kind of interesting because it just tells you it's just the representation of the data. You can flatten that if you wanted to, which, so you can also expand. So there's certain things that just lend themselves to certain solutions. So the expand function here, we create new nodes filling up the various different fields with or using operators or information from successful function calls from successors from above it, or for problems for creating corresponding states that we need to dissect. So depending upon which algorithm, I shouldn't call it an algorithm, which approach you take in terms of the knowledge representation, this is, again, not the data structure that you're storing it in, but the way you're representing the knowledge. And the knowledge isn't a number, it isn't, it's information associated with states. If you're talking about a state-to-state or a multiple-state transition, you're keeping track of all of the different states. Depending upon what you're using, in terms of the algorithmic approach, you're going to get an efficiency score. The efficiency score is going to be how fast is this technique. What we're concerned with, especially with computer science, when we study data structures and algorithms, data structures is pretty easy. It's just how you're going to store the stuff. The algorithms, how you're going to manipulate the stuff. We're looking at big O notation, we're looking at efficiency, we're looking at, well, this algorithm works, but that algorithm works too, but this one's faster than that one. When you get into AI, it's really critical, because now you have to worry about, this is a real-time system. If we put in a traveling salesperson algorithm inside of a GPS system, no dice. We probably, customer would wait there 5 hours for the thing to actually compute the best route. So instead we would apply an artificial intelligence solution to that that says, okay, forget about algorithms, forget about traditional computer science. Let's guess. And they're guesstimates. The guesstimates are actually pretty good. They come out pretty good, but they're not accurate. They're not 100% accurate. But we don't care about accuracy because we're looking at an appliance. We're looking at a toy. And you know those things are wrong because it's taken you down wrong paths before, wrong streets that, oh, wait a minute, there's no street called that here. And then you ad lib and you go back on track, and then it resets, and all of a sudden it has different directions for you. Oh, yeah, here we go. Like, oh, yeah, forget that. Or it takes you down like this really weird way of going, and it's like, I wouldn't do that, you know, especially if you know the area, which is kind of interesting. I've done that before with GPS programs. You know, you put in your own home address, and I know how to get home. It takes me down some convoluted little streets that go nowhere, you know, and I'm like, I could have gone there a lot faster another way. Because it's not the best, it's approximation. Why is it approximation? Because we can't do the full evaluation. So the evaluation of searching strategies works with the search strategy that's defined by picking the order of the node expansion. And then we have the criteria for judging it. So the search algorithms are commonly evaluated according to the following 4 criteria. Completeness, that's probably the most important. Does it always find a solution if one exists? Because that's what we want. Time complexity, in terms of how long does it take for the function, given the number of nodes? Is it feasible in a real-time situation? Space complexity, which is also a problem, especially with mapping. How much memory does it require? And then optimality, you know, does it guarantee the least cost solution? So in an AI solution, we make a compromise, and we come up with something that's acceptable as an answer, which is what you're doing in software development for the most part as well. So it's not those people who like numbers and discrete final values and they want to know the correct way of doing something, then they're frustrated with artificial intelligence because that doesn't exist. It's all approximation. So time and space complexity are measured in terms of B, the maximum branching factors of a search tree, the depth of the least cost solution, and then the M for the maximum depth of the search tree might be infinity, actually, depending upon how you're searching. So if I go through this criteria, lucky for you, you just have to know the certain criteria. You don't have to calculate it. Because if you were judging, you know, different solutions, this is some of the criteria you'd actually have to go through and calculate, you know, just to be fair, to be accurate. So in terms of the complexity, why worry about complexity of algorithms? Well, in other places, it doesn't really matter. In real-life applications, it does matter. It affects the usability of the solution. So because a problem can be solvable in principle doesn't make it too long to solve in practice. So it might be too long. So it may take it too long, which is why you can't apply a traveling salesperson algorithm to a GPS program. It's not going to work. You can also evaluate, or how would you evaluate the complexity of the algorithms? Well, most analysis can be done with estimated time, or the number of operations necessary, the number of loops necessary for solving something in terms of an instance of n, given when n tends towards infinity. So there's ways of estimating it out. And here, if you look in the book on Appendix A, this is an abbreviation of the book that I've ordered for the course. You would see in Appendix A, there's actually a bunch of statistics in terms of complexity ratios, how to measure it, what to expect in terms of efficiency. So there's a traveling salesperson problem here, and the traveling salesperson problem is a nice one to look at because it's been a challenge since the beginning, and no one's really conquered a easier way of calculating it. It's a very complex with a very long running time, not very efficient. So there are n cities with a road of length L joining city I to city J. The salesperson wishes to find a way to visit all the cities that in an optimal of 2 ways, each city is visited only once, and the total route is as short as possible. So the specifications here are the true traveling salesperson scenario, which is different from some of the other examples I gave you and some of the other definitions I gave you. So the problem is kind of twofold. If you want to consider you're only going to visit the city once, rather than being able to backtrack, it makes it more complex, actually. So this is the true hard problem. So this is a hard problem. The only known algorithm so far to solve it has an exponential complexity to it. So the number of operations required to solve it grows exponentially with the number of cities, which makes the search space too much to handle, essentially. So, given the complexity there, it's an age-old problem, and you'll get that if you take a computer science algorithm course. That's the first thing they'll tell you is traveling salesperson problem, most difficult in terms of complexity. It's only because of the exponential growth that exists with the problem, and it's because of the search space. It's like counting needles in a haystack. You know, it's pretty complicated in terms of the search space. So what is exponential complexity hard by definition? Means that the number of operations necessary to compute the exact solution of the problem grows exponentially with the size of the problem. So here are the number of cities. And these are just some examples of how it grows. Which is why the purpose of mentioning all of this stuff, which is why you cannot apply traditional computer science algorithms to artificially intelligent solutions. Not feasible. Problem doesn't work. Because the first time students take this course, they go, oh, it's just applying an algorithm. That's what we're talking about. No. If you do that, you're looking at a program that never comes back with an answer. A GPS program that's not going to work for you. So one of the best solutions to this is a genetic algorithm, actually. And I'll show you that technique, and you'll see how complex that is, but compared to this complexity, it's nothing. Because a genetic algorithm, and just to tell you what, just to give you a feel for how that's done, not a tree, not a matrix, but essentially taking a first order of natural selection. If I had a group of people, this is the example I like to use, and it's kind of a little bit of a tangent, but it kind of gives you the perspective of how can we accomplish that. So I'm looking for soccer players, and I want soccer players. I want to pick the best soccer players, and I have all this room full of people here. So if I were going to find a solution to this problem of selecting the best soccer players out of everybody in here, I'd look at the criteria of the strengths that I'd want with these players. One of the strengths, I want you to run. So I'd take and I'd put you all around the track, and I'd say, okay, who can run 5 miles? So the people who finished the 5 miles would come back, and that would be my new group. And then of those people who finished, I'd say, well, how many people can kick a ball? All right, so I throw a ball out and see, okay, so the people who can't kick a ball are discarded. Now I have people who can run and people who can kick a ball. And then I take this criteria and I go, okay, now how about people who can, I don't know, flap their arms up or whatever, you know, and then I find those people. And then I go through criteria, and I weed out the top search space. And then I randomly put in and I insert in some mutations. What if I took that person and hybrid it with that person over there? What kind of qualities would I get? And here's the combination. Okay, how many of these people have this quality? You guys do? Okay, so you guys are there. And it's survival of the fittest, essentially. And it comes down to a small group, possibly one person who's the best soccer player, given all of the criteria. That's a genetic algorithm. That's what we're going to be doing. And that's a classic AI solution. We can do that with the cities, believe it or not. By looking at the distances between all of the different cities, we can weed it out. So we discard 90% of the paths, and we only have one path left. And we can find the path that gives us all of the city locations by getting rid of all of the weak qualities and all of the other paths. And it's a weighted criteria, and it's done through natural selection. And it goes from, and this is the same thing you do when you compare genes from genetics. You look at combinations, and then some combinations are possible, and then some aren't. As an example, if you wanted to think about, well, weeding out everyone with blue eyes, or finding the blue eyes, that combination is kind of rare. So how do we know that? Because we can take genetically and analyze the gene combinations to know that brown is dominant over blue. So then we can kind of figure out statistically what the percentage is going to be, so we can estimate out, you're not going to have any kids with blue eyes. Or your generation is going to have it. And they can actually do that with diseases now, too. Actually, they can tell what you're susceptible to getting given your grandparents and your parents' generations, and what goes through the father's line and what goes through the mother's line because of the genetic correlations. There's programs out there that you can actually go and look at. If you know all the history, which is the problem, nobody knows all the history. You know all the history, you can actually pretty much see where your destination is. You're going to have lung cancer. You're going to have something else, a heart attack. You're going to have, and because it's all genetically linked, and it's pretty accurate, actually. And most of modern base medicine in the U.S. is based on those statistics. So you go in and they say, hey, what's your family history? They take the analysis that's already been done on this, the known information, and they say, oh, we should give you this test because there's a highly likely chance you have this. So they can kind of weed you out. So you can take that same analysis, apply it towards non-medical problems, apply it towards a traveling salesperson problem, apply it towards the Olympic Games, finding the Olympic players who can, and then there's games, there's a football thing that weeds out genetically different types of players. You can figure out, well, you can apply the analysis essentially to any problem as long as you have a big data set and you have the ability to put criteria and find a weeding system or a pooling system that works with it. So, and I'm going to show you how to put the framework together for that. There's a systematic approach with a couple of different steps that we'll go through. And you're going to come up with your own solution for the traveling salesperson problem. So, all right, so we've been staring at this slide. What does it say? So in general, exponential complexity problems cannot be solved for any but the smallest instances. Yeah. If you have a very small data set, you can solve problems with traditional algorithms, but are they even worth solving at that point? They're not going to do anything for you. So I'm going to skip some of the complexity stuff because this is not an algorithm course. And you can read through it. It starts around slide number 61. Gets through the polynomial time problems and log the ends and the big O notation and what all that stuff means, and NP complete hard problems. And most of you have already had this stuff from algorithm courses that you've taken in computer science programs. If not, don't worry about it. It's not part of this class and you're not responsible for it. So complexity in the human brain. Computers are close to human brain power, or are they? Which has been the age-old question ever since the Turing test. It's like, can you really take a computer and can a computer match it up? Interesting thing is that there are some things that computers do better than humans. There's a lot of things. Calculations, for that matter. Computers do a much better job than humans. And there's no learning curve. You just plug them in and they work. So, unfortunately though, humans reason, humans think, humans feel, they have senses, and they're much better with perception than computers. So, you got your choices. So you can pick current computer CPU processing power, and it's kind of interesting because if you look back historically, the first calculator did simple algebra, and it took it, the computer, if you go back through the archives and read, and there was something actually on Channel 9 not too long ago that compared modern day computers with today and the exponential growth. And there's a bunch of, Moore's laws and all this stuff that people have been doing for years. It said, computer power doubles, processing space cuts in half, semiconductor chip sizes go in half every year, and all these other statistics that you think about. The first computer took, 5 or 6 minutes or something to do a basic math problem. And the computer itself took up an entire room. Now we have electronic clocks, and we have digital devices that do math problems instantaneously that fit on your watch, or they fit, in a pencil or something, like really small. Even little key codes for the key fobs are doing calculations automatically for you every second. So if you think about that power, AI holds a lot of strength in terms of revisiting every year, so which is why the age-old problem hasn't gone away. We're still trying to make computers think as fast as humans. The only problem is humans start getting more complicated. So, and then which human are you going to try and mimic in a computer, which is another problem. So comparing the two, you can kind of see the difference. Still a lot of improvement needed for computers, but computers clustered, some clusters come close. Well, clouds come close too, but computer clustered and brain power put together. But actually, believe it or not, as we go through the years, computers are definitely catching up to humans in terms of that concept. So remembering the implementation of search algorithms and going back to this little pseudocode I talked about here, we have that queuing function. We're looking at inserting elements, and we're looking at queuing and determining the order of the node expansion in terms of our problem solution. So encapsulating state information into the nodes this is basically a repeat of the slide I was showing you a few minutes ago. In terms of the evaluation, we're looking at these particular, so remembering the components that we're trying to consider. This is where we get into what I'm calling approximations. So AI is dealing with approximations. So in our complexity analysis, we do not take the built-in loop detection into account. So we're not necessarily looking for loops. Instead, we're looking for approximate solutions. The results are only formally applied to a variant of different algorithms without looping checks. So studying the effects of looping checking on complexity is hard. So we're not going to look for loops. So the overhead of checking may or may not be compensated by the reduced number of size of the tree. So we're approximating for the most part. So we're not as accurate as we probably could be. Also, our analysis does not take the length or the space of the represented paths into account. So we don't really consider how long are we going to go down this route in terms of the path that we intend to follow. So we can cut out a lot of that information. So it's just as a quite note, just a little bit of note in terms of, not being as accurate as you might think, because it's not about accuracy, it's about finding the optimal solution or getting to the goal. Alright, so we have 2 chapters in the book. One's on informed and one's on uninformed searches. And they're search strategies. So we use only information available in the problem formation. We don't consider anything else that's not part of the problem situation, which is kind of interesting because then that focuses the search a little bit. And again, it narrows the thinking, but it leads us in a more directed fashion. So we have depth first, uniform cost, breadth first, depth limited, and interactive deepening. If I can say that correctly. I choke on my words. So what I'm going to do is going to give you a brief definition of these without boring you too much, because this material gets a little dry. And I will tell you, I will save you because, as I mentioned before, I'm not a tree person. I don't like trees. I like lists. So. Not my favorite subject either. So breadth first search. What are we looking at? Expand shallowest unexpanded node. So in terms of the implementation, the queue would start at the beginning, Arad, which is the beginning node, the root, and put successors at the end of the queue. So if we're traveling from Arad to Bucharest, we're going to expand out this way. So we see the 3 cities here. I'm not going to pronounce those cities, by the way. So I'm going to call Arad A. From point A to point B, we're getting from the 3 different cities there from the first. And then we're going to expand out from the left to right in this particular fashion. It doesn't really matter. It depends on the order in which we build the tree is going to be the order in which we're going to read the tree. So just like traditional data structures, actually, the formation of the tree is the basically intended reduction in terms of how we're going to read it. So properties of the depth first search. In terms of completeness, time complexity, space complexity, and optimality. Completeness, meaning does it always find the solution? And this is a review of what we saw before in terms of the criteria. We can fill in the blanks. I'm just going to fill it in for you rather than going through all that stuff over again. Completeness, yes. If B is finite. If there is a B, we will find it. Because it's not what I'd call a fast way of finding it, because we have to expand everything. And it's all done in the same level by level by level. Time complexity, it's exponential to D, which is going to be how many levels that we're going to have. Space complexity, well, it keeps every node in memory. We have to analyze after we've expanded everything to follow it through. Optimality, yes, assuming the cost is equal to 1 per step. Given the search space, how big the tree is, it could be optimal. So, why keep every node in memory, however? So this particular first technique is just going to load everything, put all of the nodes in memory. Why do it? Avoid revisiting already visited nodes, which may already be yielded infinite loops or unavailable. Because some of those paths aren't going to lead us to B. They're just going to lead us astray. Or they're going to loop us around. So time complexity in terms of the first breadth, the depth first search. If the goal node is found in the depth D of the tree, all nodes up to that depth are created. Once the node is found, it's supposed to stop. So thus it's to the depth of the tree in terms of its complexity, which makes it ideal for some situations. It makes it not so optimal if you know it's going to be further down. So if you know you're not going to find it easily, then and you have a large search space, not such a good idea. It's going to totally block up your memory. Largest number of nodes in the queue is reached by level D of the goal node. So the queue here contains all the way up to the red, and then we have the G nodes, thus 4 levels. 1, 2, 3, 4 levels. So. Then we have the uniform search. So we expand the least cost unexpanded node. Instead of expanding all of them, we take the least cost, which is going to be the shortest predicted node. In terms of the implementation, we look at the inserting in the order of the increasing path cost. So the queuing function keeps the nodes listed sorted by increasing path cost, which means you have to calculate the path cost. So we expand the first unexpanded node, hence the smallest path cost is achieved by looking at the different path costs and only expanding them in the order that we need to. So it's a refinement of the depth first strategy. It's still starting at the top and it's expanding downward. And it's basically the breadth first, which equals the uniform cost with the path cost, which is equal to the node depth. So if we look at this, we've got the straight line distance between, and this is what you're actually going to get in that one of those assignments that you're going to do. You're going to get the distances, and I don't give you cities, I just go A, B, C, D, E, F, G. 26 cities by 26 cities with path costs that go between the cities. And we can figure out, well, given the path costs, if we put them on the graph, which you see here, we can add everything up and pick the shortest ones first. And so we're only going to look at the shortest ones. So here we have a path cost of 75, 140, and 118. Well, that would be the 75 first. And we go 75, 71, and then we get to take the next one. So it's the depth first, but we're looking at the priority of the path because we're thinking, are we going to find it? Are we going to find it? And then we're going to go to the next level. And then we're going to do the same process over again, starting with the shortest path. But we only know it level by level. We haven't looked ahead. This is an uninformed search, by the way. What makes it uninformed is that we haven't looked at everything. If we looked at everything, then that's why I don't carry my phone, by the way, because it's irritating. If we look at everything, then it's not an uninformed anymore. It's an informed search and falls into a totally different category, and we apply a totally different technique to this. So it's not going to be the same. So in terms of its properties, for completeness, yes, if the step cost is larger than or equal to the length of the larger than 0, which means we actually have somewhere to go. Time complexity, the number of nodes of G is less than or equal to the cost of the optimal solution. Space complexity, very similar in terms of that. Optimal, yes, as long as the path cost never decreases. So it never goes small, it always stays at the same level, which is going to be essentially what we're going to use to determine the next step in the unfolding. So G of n is the path cost of the node to remember, B is the branching factor, and D is the depth cost solution. We're looking for the smallest D in this particular case. So in terms of the implementation, we initialize the queue with the root node and build from the start state downward, the same thing as we were doing before in the breadth first. Repeat until the queue is empty, and then the first node has the goal state in it. And we can kind of find out from the first node which direction we're going to actually follow. So we remove the first node from the queue from the front of the queue, expand the nodes, find its children's, reject it. This is the algorithm that would be implemented, which is kind of the same way that you would implement a traversal algorithm from the tree, looking at the shortest distance as its criteria. So once the goal is reached, return successful, otherwise it's failed and it says, hey, there's no way of getting from point A to point B. But there should be something. So in terms of a caution here, the uniform cost search is not optimal if it is terminated when any node in the queue has got its goal state. So depending upon how big the queue is, it's not very optimal if it finds it too quickly, because then you've got a lot of overhead in the setup. So uniform cost returns the path with the cost of 102 in this particular case if any goal node is considered in the solution, while there's a path with a cost of 25, it's a little bit shorter. So it's not most optimal in that particular case, especially if it finds a goal with a longer path than what was in there before, because it goes under the theory that you're going to stop looking. It's kind of like how we go bargain shopping. We find something, oh, this is pretty cheap, and we buy it, but we don't know that if we just looked for 5 more minutes, you know, like when you're through eBay or something, look, we can find it if we just spent a little bit more time and exhausted our search a little bit more. So it's fast, but it's not the most optimal. So you can quickly buy something, but you won't necessarily get the most optimal price for it. But then again, the cost of waiting might, in an eBay search, however, the cost of waiting might cause you to lose the first one. So, and then you'll be paying more in the end. So, well, that's an artificially intelligent kind of way of thinking because you're a human. Well, I shouldn't say artificial, it's a human way of thinking in terms of logic. So, can you put that into a eBay buying search agent? Probably. Actually, there's programs out there that do aggregates for you that come through and say, this one's gonna, this eBay auction's gonna end in 5 minutes. Do it now. Automatically bid on stuff. So, which defeats the purpose of the free economy and the free bidding system when you have computers out there doing it. Anyway, loop detection. In order to detect a loop, you have to actually load everything into memory. So in class, well, we didn't see this because I didn't do it, but no looping detection was performed with the last example that we looked at either, and no queuing to nodes. So if you don't do looping detection, you can save yourself some time and you have an approximation, which means you don't have a guaranteed complete path, but it may not necessarily be your criteria. It might not necessarily be something that you have to think about, but note that loop detection is optional in most cases, and it gives you an approximation without it. Alright, so the rest of this, we're almost done with it, believe it or not. I'm not going to go through the loop detection example, but if you want to use this, this is lecture number 3. What we're looking at here is our examples or illustrations of uniform search strategies applied towards problem solutions. You're going to see one in the midterm, actually. So you'll be able to do this on your own. It's also in chapters number 4 and 5, I believe, of the book, but I have to bring the book in tomorrow so I can verify that. But this classic example, and this is taken right out of the textbook, actually. I've had to do a breadth first search, and then we have a uniform search cost that can be calculated from this. So we can apply the same scenarios to different searching strategies to figure out, well, why is one faster than the other? Is one more complete than another? And then you can compare them across the board. The book does an excellent job with that, actually. So I'm not going to bore you with that because this is where it could get really, really dry. So I'm going to kind of thumb through here, tell you what's in here. You can go through stage by stage in terms of the traversal. I'll have another exercise for you to do that will probably not occur until the next weekend. So it's not going to happen this weekend. But I'll have some easy, draw it out, follow this pattern with a reminder of what the pattern is so you can apply it. And then on the midterm, on Sunday, I'll go over that. But you'll see you'll have some practice with that as well on the midterm. So I'm going to kind of thumb through this to sort of just see if there's anything else in here that I want to cover. I'm not going to cover the depth information at this point. It's all basically comparing the search from the two strategies that I showed you so far. This is a reiteration of the first, going through with a real example. So that is all for this particular, which is lecture 3 that we needed to cover. So I'm going to stop the video momentarily. We still have one more exercise to go over. So I'm going to stop this one, and then we're going to hit an exercise overview so I can separate this out.